Hi. In this video, we are going to continue our section on combinatorics. We are going to look at some properties of binomial coefficients. So, as you might be aware of, if you have a binomial expansion x plus y power n, it can be written as a general summation k is equal to 0 to n c k x power n minus k and y power k. Now, this n c k is the binomial coefficient, and there are lots of properties that these satisfy. So we'll start off with that. So first one is obviously the definition of NCK, which is n factorial by k factorial n minus k factorial. And we know that NCK is equal to NC n minus k. That is the first property. And you can also expand it and write it like this: n into n minus 1 multiplied till n minus k plus 1 by k factorial, right? Then the second thing that we look at here is the recursion formula, which is Pascal's identity. Recursion formula. So in Pascal's triangle, we have sum of any two elements which are consecutive elements in a single row is equal to the sum of the element beneath it, directly beneath these two elements in the next row. So that identity is written like this: n minus 1 ck plus n minus 1 ck minus 1 is equal to nck. There are many proofs of it. If you just use the definitions of NCK and expand this left-hand side, you can eventually prove that it is equal to NCK. So I'll not go into that. That's pretty easy. Then the third property is unimodality. And here we talk about which binomial coefficient is largest. So we have, if n is even, this is the set of inequalities that we have. NC0 is less than NC1, less than so on till less than NC n by 2, which is greater than NC n by 2 minus 1, and so on till NC n minus 1 greater than NC n. So basically this term NC n by 2 becomes the largest term, and also it is the middle term here. This is the largest binomial coefficient if n is even. If n is odd, we have this situation: NC0 is less than NC1, less than, here we have NC n minus 1 by 2, which is equal to NC n plus 1 by 2. And these are greater than the other terms ahead of them. So greater than NC n minus 1 and greater than NC n. So basically now we have two middle terms, and these are equal in value when n is odd, right? So we can combine these two things in a single formula, say the maximum binomial coefficient becomes NC n by 2. Here this is the ceiling function. What is the ceiling function? Just like we have floor function or GIF function, GIF was greatest integer less than equal to x, right? The ceiling function is least integer greater than equal to x. Least integer greater than or equal to x. So it is the ceiling function of n by 2 here. So that becomes the maximum term in a binomial coefficient, right? Now we look at some other properties which are very standard and interesting. So let's look at this one first: NC0 plus n plus 1 C1 and so on till n plus k ck. So what is happening? You are adding 1 to the subscript and the superscript. Both of them are getting increased one by one till n plus k ck. This will be equal to basically n plus k plus 1 ck. That is the property. How do you prove this? We do it by this method. We can say NC0 plus n plus 1 C1 is the same as n plus 1 C0 plus n plus 1 C1. Because n plus 1 C0 is same as NC0. And this becomes Pascal's identity. So this is equal to n plus 2 C1. Now you take n plus 2 C1 and the next term here, which was n plus 2 C2. So you have n plus 2 C1 plus n plus 2 C2, which will become n plus 3 C2 by Pascal's identity again. And here the term was n plus 3 C3, and you keep repeatedly adding. keep adding repeatedly and you will end up with this result. So you can try that out yourself and check this proof, right? The next property is some obvious identities for binomial coefficients. NC0 plus NC1 till NCn is 2 power n, NC0 minus NC1 plus NC2 plus minus 1 power n NCn is 0. So these are obvious from the expansions of 1 plus x power n equal to summation of NCr x power r goes from 0 to n. In this, if you put x is equal to 1 and minus 1, you will get these identities, right? Okay, the next property is this one. MC0 NCk plus MC1 NCk minus 1 and so on till MCk NC0 will be equal to M plus 1 NCk. So this is also a standard identity. It is known as van der Monde's identity. And the idea is you take two different series, 1 plus x power n and x plus 1 power m. So 1 plus x power n expansion will be C0 plus C1x plus C2x square and so on till Cn and here this would be MC0 x power m plus MC1 x power m minus 1 till MCm x power 0, right? If you multiply the two series together, you will get 1 plus x power m plus n and you will have to do product of these two series and you have to check the coefficient of x power k on both sides. Coefficient of x power k from here is simply m plus n c k and coefficient of x power k here will be the product of C0 and ck here. NC, actually I should have taken this as m and this as n and then you would get the series. So just check it out. The product of two different series, one of the series has to be reversed and then multiplied. Then you will get that MC0 into NCk plus MC1 into NCk minus 1. This series of terms always has coefficient of x power k. This is coefficient of x power k. This is also x power k term and so on. So that is the way in which you can prove this identity. You can try that out yourself. It is pretty straightforward. One special case of this identity is when you have NC0 whole square plus NC1 whole square plus NCn whole square, right? So here what you're saying is this is equal to 2NCn because what you're doing is m is equal to n, right? And actually k is also equal to n, right? So from the previous case, you can again prove this. Take two different series, 1 plus x power n and x plus 1 power n, and expand it, C0 plus C1x plus C2x square, and so on till Cnxn. And this side it will be C0xn plus C1 x power n minus 1, and so on till Cn x power 0. When you multiply it and check the coefficients of x power n terms, you will realize that it is C0 square plus C1 square plus C2 square plus Cn square. That is the coefficient of x power n in the product of this series and this series, right? So that should be equal to coefficient of x power n in the product of these two, right? So that will be 1 plus x power 2n, which is equal to 2nCn. So that is my proof, correct? Then a couple of very useful identities which are used in summation. So this identity is NCk is equal to n by k, n minus 1 ck minus 1. This is a very important identity, useful in converting summations into a form that is more amenable to adding. So basically you'll use it like this, k times nck is equal to n times n minus 1 ck minus 1. This is what you will be mostly using. And the other one is this one, nck multiplied by kcm is equal to ncm multiplied by n minus m ck minus m. Now, how to prove this? You should just expand this whole thing, LHS and RHS, according to the definitions of the combinatorial coefficients. Once you expand and multiply, you will realize that they will be equal. It's a pretty straightforward algebra proof, so I'll not show it here. What we'll do is we'll use these in questions. Okay, so let's start off with some basic ones. So question 1 is this: find summation of k is equal to 0 n k times nck, and also summation of k is equal to 0 to n k square times nck. Right. So there are many ways to do this. There is a method by differentiation. So basically you can take 1 plus x power n is c0 plus c1x plus c2x square and so on, cn xn. And you can differentiate this and write it as n 1 plus x n minus 1 is equal to c0. C0 is completely gone because it's a constant. So you'll get c1 plus 2c2x plus 3c3x squared plus ncn x power n minus 1. Now you can put x is equal to 1 on both sides. You will get n into 2 power n minus 1 is equal to c1 plus 2c2 plus 3c3 plus ncn. So that is one way to do this. Another way to do it, however, would be using the summation formulas that I showed in point 8 and point 9, right? Point 8 ideally. Similarly, this question can be also be done by differentiation. You can take this function and do a do a differentiation here, then multiply it by x. At this stage, multiply the both sides by x. So what we'll get is this: n into x into 1 plus x power n minus 1 is equal to c1x plus 2c2x square, right, plus 3c3x cube and so on, ncn x power n. And now differentiate again. So you'll get c1 plus 2 square c2 plus 3 square c3 x square, and here it is x, and n square cn x power n minus 1. So you take the series, differentiate it once, then multiply by x, then differentiate it once more, and you end up with this situation. So left hand side here I have to differentiate, it will become n 1 plus x power n minus 1 plus nx n minus 1 into 1 plus x power n minus 2. That is equal to this. And when you put x is equal to 1 on both sides, you'll get n into 2 power n minus 1 plus n into n minus 1 into 2 power n minus 2, right? And here you can take n into 2 power n minus 1 common, and you will get basically 1 plus, no, you will get 2 plus n minus 1. So that will become n plus 1. So the answer is n into n plus 1 and 2 power n minus 1 is equal to summation of k square nck. K goes from 0 to n. So we have done both of the problems by differentiating, but what I wanted to actually show you was not using differentiation, but using our summation formulas. So summation k times nck, k goes from 0 to n. Now what you can do here is using formula 8. What was formula 8? It was nck is equal to n by k, n minus 1 c k minus 1. So therefore, k times nck is equal to n times n minus 1 c k minus 1, right? And if you replace this now with n minus 1 times, replace this with summation k goes from 0 to n times n minus 1 c k minus 1. The n can go out of the summation, and you get summation k is equal to 0 to n minus 1 c k minus 1. This summation runs from n minus 1 c minus 1, which is not defined, so we can call it 0, n minus 1 c 0 till n minus 1 c n minus 1, right? When you put k is equal to n, you get this. So this sum is simply 2 power n minus 1. So you get the answer is n into 2 power n minus 1, right? So that is one way to do it. The other problem can also be done by this method. Summation k square nck we had. We have to find this. So think about it. K square can be written as k into k minus 1 plus 1. So therefore, k square nck is equal to k into k minus 1 nck plus nck, right? Actually, I'm wrong. K square minus 1, this is plus k. So this will be a plus k nck. So if you have summation of k square nck, that can be split into two separate summations, k into k minus 1 nck plus summation of k nck. And we have already done k nck summation in the previous screen. So that is n into 2 power n minus 1. This we know already. We just have to find this now, right? Now, how do I do this? The way to do it is simple. We say that k times nck was equal to, we know k times nck was equal to n times n minus 1 ck minus 1, right? Correct. Now, similarly, we can say that nck was basically n by k n minus 1 ck minus 1. So n minus 1 ck minus 1 would be equal to n minus 1 by k minus 1 n minus 2 ck minus 2, right? Because of this result, if you replace n and k with n minus 1 and k minus 1, you should get this result, right? So from here, what we get is, we can replace n minus 1 ck minus 1 with n into n minus 1 by k minus 1 n minus 2 ck minus 2, right? So what we get ultimately from here is k times k minus 1 nck is equal to n times n minus 1 n minus 2 ck minus 2, right? Now this is the crucial thing, because we have a summation over k into k minus 1 nck here, and we can convert that into this summation, which is much easier because n minus 1 is a constant, it comes out, right? So basically, summation of n minus 1 n minus 2 ck minus 2, where k goes from 0 to n, is simply n minus 1 into 2 power n minus 2. You can check that this comes out of the summation, and this is a straightforward series. When k goes from 0 to n, it is going n minus 2c 0 to n minus 2c n minus 2, right? So this technique of summation, where we use the formulas to convert the summation into something else, is something that you should learn. So that is what I wanted to focus on. Obviously, there are other techniques also. Integration, differentiation can be used, but we wanted to show you this one. The next question is this: prove that k is equal to m to n summation of nck into kcm is equal to 2 power n minus m NCM. Now here we will use the result NCK into KCM. This is formula 9, which is equal to NCM N minus M C K minus M. So if you write this result like this, the summation of this term, summation over K goes from M to N of these two becomes NCM times N minus M C K minus M. Now here we can take the NCM out common because it doesn't have a K. Summation is over K, so we can take it out common, and we have summation K goes from M to N, N minus M, C, K minus M. So basically this is a simple summation. This is expanding it. You will put K is equal to M, it will become this. Then you will put K is equal to M plus 1. It will become 1, and so on. Finally, K is equal to N, it will become N minus M, C, N minus M, right? So this is simply 2 power n minus m. So our question is done. NCM times 2 power n minus m. Question is done because we are using the correct formula here, this formula. So that's why I wanted you to focus on the two results, 8 and 9, which are very important in summation. So that is one thing to learn from this video. The next question, I will show a proof by a different method to prove the identity. Summation I goes from 0 to n, NCI, n plus ICI is equal to summation I goes from 0 to n 2 power I multiplied by nci whole square. This is the identity that we wanted to show. So what we will do here is we'll do it by the combinatorial method. So we'll do it by counting in two different ways. So let's set up a counting problem whose solution will look like this, right? So let's say there are n women, n men, and n women from which n people are to be selected, n people are elected to form a committee, to form a committee, and then from the n people, elect several women, one or more than one women, to form a leading group, to form a leading group for the committee, for the committee. The number of women in the leading group is not specified. Number of women in leading group could be greater than or equal to 0. Obviously, it can be up to n, greater than equal to 0, right? So how many ways to do this? How many ways can we do this? So first you have to select a committee of n people from n men and n women. And then among the n people, you have to select several women to form a leading group, right? And that leading group can have more than or equal to 0 people also. So what we'll do is we'll solve this counting problem in two different ways, which will help us prove this identity. So the first method of counting this is like this. For 0 is less than I is less than n, there are n minus I ways to elect n minus I women from all the women, to form a leading group, right? To form a leading group. So what we have done is we have selected n minus I women from all the women, which are n, in nc n minus I ways to form a leading group. So right now our leading group has n minus I women. And now the remaining, there are total how many people remaining? There are n plus I people remaining, which consists of n men and I women, right? N plus I people remaining. And out of those remaining people, you can select I members, right? So these will be the remaining members of the committee which are not part of the leading group, right? So what you can say is that can be done in n plus ICI ways, right? So the total number of ways to select the committee and the leading group will be the product of n minus I multiplied by n plus ICI, right? Now n minus I is equal to NCI. So here, this is what it is. It is n minus I multiplied by n plus ICI. So this is for I is equal to 0. You could have a committee of n women if I is equal to 0 who lead the group, or you could have a leading group of n minus 1 if I is 1, n minus 2 is I is 2, and so on, right? So the first method, what we are doing is we are doing the summation of n minus I, n plus ICI, and I goes from 0 to n. Here, this is helping us to form a leading group of women, leading group of n minus I women. And this is selecting remaining members of the committee, selecting remaining members of the committee. right? So that is one way to solve the problem. Now what I want to do is solve the same question in a slightly different way. Okay, so we'll focus on the second way now, second method. So here what we'll say is for 0 is less than equal to I is less than equal to n, there are nci and n minus I ways to select I from women and n minus I from men, respectively. And basically, we have, if you multiply these ways, NCI into NC n minus I, you basically get NCI square n person committees. Right now, we have just formed the committees, and each committee has I women. N person committees containing I women, right? So we have not yet formed the leading group, right? We have just formed our committee. Now, in each of these committees, there are I women. So the I women can, only the women can be part of the leading group, right? So if you want to find number of ways to form a leading group from the I women, from the I women, that will be the number of subsets of the I women that are possible, right? So that is clearly 2 power I subsets of I women are possible to form a leading group, right? So once you have formed the committee in this many ways, you can form the subsets or leading groups in this many ways, 2 power I into, this is the total number of ways to do it, right? And this is for a single value of I. If you sum it over, I goes from 0 to n, you will get all possible ways of accomplishing this task, right? So in the second method, it is clear this is the total number of ways to do this. And the first method we had summation I goes from 0 to n, nci, n plus ici, right? So basically by two different combinatorial arguments, we have shown that we have calculated the same thing, right? So therefore we have proved the identity. Obviously the identity can also be done by other normal standard algebra methods. But what I wanted to show you is how to do it in a combinatorial manner, right? So that is sometimes useful in problem solving. So hopefully you learned something from this video. In the next class, we will discuss correspondence and recursion as tools in combinatorial problem solving. So that's a good place to stop. I'll see you next time.